Hello, Professor Sargent here with you again for another Math 101 flipped classroom lesson. This is on our last section, section 10.6, but it's only, it's being split over 2 days. So this introduction will only cover what's on the day one assignments. We're going to talk about solving equations with variables in the exponent or variables inside of a logarithm. And you might think, well, why are we talking about solving equations with variables in the exponent when we've already seen that? Well, I don't see an easy way to write 18 as a power of 3. It doesn't matter that it's a multiple of 3. I don't see how to write it as a power. So that's 3 to the x power, not 3 times x. Since 3 squared is 9 and 3 cubed is 27, we've just jumped past 18. I expect that answer for x is going to be between 2 and 3. And here's what we can do. Take a logarithm of both sides, either common log or base e, the natural log. Either one would be okay, because we know that we can write the left-hand side here as, using the power rule, we can bring that exponent out in front. There we go, so x times logarithm. And whatever log of 3 is, it's a number. And whatever log of 8 is, it's just a number. So if you think of that as a coefficient for x, let's see it written that way. Whatever that is equal to as a number, it's multiplied to x. So I can divide by that coefficient. X will equal the log of 18 over the log of 3. If I'd done the natural log of both sides instead, it'd be natural log of 18 over natural log of 3. Either way, I'm going to look at that on the calculator. What I've typed here is 2 possible ways to give an exact answer. If you are asked for decimal approximation, then go further. You find the log button here. Oh, hold on a second. There, now you should be able to see the calculator. Log button here, log of 18 divided by log of 3. And remember, I said I expected an answer between 2 and 3. If I use natural log, which is just below it, natural log divided by natural log of 3, same result. Now, if I round that to 3 or 4 places, I'm going to go to 4 places. If I take 3 to the power 2.6309, then I should get close to 18, 2.6309. Since I've gone to 4 places, then this to 4 places should be pretty close to 18. 17.9994, pretty darn close. All right, stick around for some more examples. All right, let's talk about some examples where we have to solve equations where the variable is either in an exponent or in a logarithm. For this first one, I'm going to give you 2 options and talk about the pros and cons of those options. But before we do that, take a look at that equation. 6 to the x equals 2. 6 to the first is 6. 6 squared is 36. If you take any power of 6 where the power is bigger than 1, we're going to be getting an answer bigger than 6. And 6 to the first again is 6. So I'm expecting an answer to this that is smaller than 1, perhaps even negative. On this first option, I'm going to show you the approach that I learned, which would be to take the logarithm of both sides. Somehow I got used to taking the natural log of both sides. It would not matter if you took the common log of both sides, i.e. base 10. Now, by this, I can take the left-hand side and apply the power rule, which would allow me to bring that exponent of x, the thing that we're trying to solve for, out to the front. Whatever the natural log of 6 is, it's a number. So really that is the coefficient for x. Whether you rewrite it the way I did or not, the point is, to get x alone, we're going to have to take dividing both sides by the natural log of 6. And let's put that into the calculator, find out what we get when we round to the thousandths place. So natural log of 2 divided by the natural log of 6. Natural log, got to keep it consistent. It can be base 10 top and bottom, or natural log top and bottom. It's got to be the same. And we are getting the thousandths place, that is 4 places out. So in the 5th place, we have a 5. We're going to have to round that to 3.869. 3.3869. Bring the calculator back up here. We're going to raise 6 to that power to do a check. Then when we round that, we're getting 1.9367 for our second option. We could, since the exponent with a variable in it is an exponent for a power of 6, we could take the logarithm in base 6 of both sides. And on the left-hand side, the two are going to cancel out because we have inverse functions going on there. So we're just left with x equals the log of 2 in base 6. Then to get the decimal approximation, then you're going to have to apply the change of base formula, which is what we had over here on the left. We would change that to the natural log of 2 over the natural log of 6, and then get that 0.3869 anyway. In fact, a little bit quicker. We could skip this line and just say, okay, we write this as a logarithmic equation because the answer to a logarithm is an exponent, so that logarithm is equal to that exponent of x. We had a base of 6, and then by a process of elimination, the argument of the logarithm is 2. Some pros and cons. We wind up still having to use the change of base formula to get the decimal approximation in option 2. Plus, what if we have both sides raised to exponents? Then what would you do with option 2? We're going to take a look at that a little bit later. So on this one, number 2, let's go ahead with option 2 and take the log of both sides in base 5. By the way, the reason this is working is because logarithms are functions. The 5 to the 2x and the 14 are equal. So that same input is going to give you the same output, even if it's written a little bit differently. On the on the left-hand side, we're going to get cancellation. So we just have 2x, no more exponent there. On the right-hand side, let's apply the change of base formula at the same time, where the denominator, or the base of the fraction, is the logarithm of the old base. And normally we'd say that we're going to divide both sides by 2, but I don't want to write a fraction inside of a fraction. So I could instead say that I'm multiplying both sides by 1/2 to get rid of the x. Now, let's put that into a single fraction by multiplying straight across. I have to be careful putting this into the calculator. I have the natural log of 14. And then when we divide, natural log of 14. And then when we divide, then we're going to want parentheses around the 2 times the natural log of 5, so that the calculator knows this is all in the denominator. Close the parentheses for the logarithm and for the denominator. This one only wants us to go to the nearest thousandth, which is 3 places out. 0.819, but then we've got an 8 after that. That's going to round that up to 0.8020. Sorry, read that wrong. 0.820, I believe is what we want to say. Yeah, 0.820. All right, where was I? Now, if we do a check on that, putting an x in here, first we would double that. Use that 1.64 as a power for 5, and we should get about 14. Pretty close. Here's the kind of example I was talking about. What are we going to do if we try to use option 2? Let me first do this by option 1. Take the natural log of both sides. Apply the power rule. Well, here you have to be careful, very careful on this left-hand side. That entire exponent is a natural log of 3. That entire exponent is x plus 5, I mean. And we have to apply the power rule for logarithms on the right-hand side as well. Usually what we see being done is distributing that number. Natural log of a number is a number, as long as it's within the domain. So some number that we're just writing as natural log of 3, it's going to get distributed the x plus 5. Now, to a lot of people, that starts to look pretty messy. Well, if you just remember, natural log of 3 and natural log of 8 are just numbers. Let's get the terms with x together on one side and terms without x on the other. So I'll subtract the natural log of 3 times x from both sides. That was 8x minus 3x. You combine the like terms and get 5x. The way you're getting 5x is subtracting the coefficients. It's almost like we're factoring the x out. Same thing's going on here. Factor that x out. And then whatever that mess is times x, it's just a number. So divide both sides by that to get x alone. So let's get that put into the calculator. In the denominator, we're going to have to be really careful again. We want it to know that entire natural log of 8 minus natural log of 3, that is the denominator. The multiplication in the numerator, that's all that's going on, so we don't have to worry about that as much. We don't have to put parentheses around that. So I won't. Around that denominator, natural log of 8, close the parenthesis, minus natural log of 3, close the parenthesis. This one was also supposed to be rounded to the thousandths place. So that's 3 places out. And that's going to round down because the 4, the place after we're supposed to round to, that's going to round that down. We're going to have about 5.600. Checking that. If we were to put that into this exponent, 5.600 plus 5, that'd be 3 to the power of 10.600. Whereas we're just putting in the 5.600 as power of 8. And it's because of the rounding that these are that far off. But still, 114,100 something. They're both pretty close. Here's the kind of example I was talking about. What are we going to do if we try to use option 2? Let me first do this by option 1. Take the natural log of both sides. Apply the power rule. Well, here you have to be careful, very careful on this left-hand side. That entire exponent is a natural log of 3. That entire exponent is x plus 5, I mean. And we have to apply the power rule for logarithms on the right-hand side as well. Usually what we see being done is distributing that number. Natural log of a number is a number, as long as it's within the domain. So some number that we're just writing as natural log of 3, it's going to get distributed the x plus 5. Now, to a lot of people, that starts to look pretty messy. Well, if you just remember, natural log of 3 and natural log of 8 are just numbers. Let's get the terms with x together on one side and terms without x on the other. So I'll subtract natural log of 3 times x from both sides. That was 8x minus 3x. You combine the like terms and get 5x. The way you're getting 5x is subtracting the coefficients. It's almost like we're factoring the x out. Same thing's going on here. Factor that x out. And then whatever that mess is times x, it's just a number. So divide both sides by that to get x alone. So let's get that put into the calculator. In the denominator, we're going to have to be really careful again. We want it to know that entire natural log of 8 minus natural log of 3, that is the denominator. The multiplication in the numerator, that's all that's going on, so we don't have to worry about that as much. We don't have to put parentheses around that. So I won't. Around that denominator, natural log of 8, close the parenthesis, minus natural log of 3, close the parenthesis. This one was also supposed to be rounded to the thousandths place. So that's 3 places out. And that's going to round down because the 4, the place after we're supposed to round to, that's going to round that down. We're going to have about 5.600. Checking that. If we were to put that into this exponent, 5.600 plus 5, that'd be 3 to the power of 10.600. whereas we're just putting in the 5.600 as power of 8. And it's because of the rounding that these are that far off. But still, 114,100 something. They're both pretty close. I'm going to use the second option, the second method that I used in a previous video for this one. Since we only have a variable and an exponent when it's applied to a base of 3, I'm going to take the base 3 logarithm of both sides. I can do that because y equals log of x base 3 is a function. So if the inputs are equal, then the outputs must also be equal. On the left-hand side, those are just going to cancel, and I have 3x equals the log of 12 in base 3. To get x alone, I could say that I'm dividing both sides by 3, but it's going to be easier to type into the calculator if I write that as 1/3 times log of 12 in base 3. Applying the change of base formula. The way I'm going to have to put this into the calculator is with multiplication that's in the denominator inside parentheses. I'll get you the decimal approximation here in a moment. I'm coming up with approximately, when we round it to 4 places, 0.7540, and in a moment I'll show you how to type that in on the TI-30. All right, we've got to put in the natural log of 12, close the parentheses after the 12, divided by, put parentheses around the multiplication in the denominator, 3 times natural log of 3, parentheses to close the logarithm, and to close the multiplication in the denominator. We're supposed to go to 4 places after the decimal point, a 10,000ths place. After that is a 5. It's going to round up that 9 to 10, carrying that over 0.7540 as previously written. And if we check that, 3 to the power of 3 times 0.7540, we should come up with something really close to 12. If we were to round to the same number of places, we would have 12.0019. That's pretty close to the 12. Now what about when we have logarithms inside of a variable? Sorry, variables inside of a logarithm. The goal on a question such as this is to first get a single logarithm and then apply the definition of logarithms to be able to solve something that looks like something we've seen before. Now we've got both of these in base 5, which is going to allow us to use the product rule for logarithms. We've seen it used in both directions. Before applying that, though, remember that the domain of a logarithmic function is that you have to be putting in positive numbers. So for the first one, we've got that x is going to have to be greater than 0. But also, from the second, that x minus 24 will also have to be greater than 0. That second one, if you add 24 to both sides, that's not going to change the direction of the inequality symbol. Now, which one of these leaves out more numbers? What's more restrictive? If you have a number line, 24 is further to the right, and x greater than 0 is going right, x greater than 24 is going to the right. You're going to be leaving off more with that second one. So we're going to go with the second one as telling us what kind of answers we're going to require. Now, using the product rule for logarithms, we can put this left-hand side back together as the product of x times x minus 24 inside a logarithm of base 5. That's going to equal 2. And if we apply the definition of logarithms, the base is 5. The exponent, the answer to the logarithm, that's the exponent, 5 squared, by a process of elimination, that has to equal the arguments of the logarithm, i.e. what was inside. On the left-hand side, I'm going to distribute the x. And on the right-hand side, do the arithmetic. Since we have x to the second power, we're dealing with a quadratic equation. And there are a number of ways that this could be solved. But the quickest is going to be to factor. It's not the case for all quadratic equations, but since that's a 1x squared, I know I'm looking for a pair of numbers with a product of negative 25 and a sum of negative 24. And two numbers that'll do that I'll put into parentheses for the x's are minus 20, negative 25 and positive 1. Set each factor equal to 0. And then you've got two linear equations to solve. Now, if I hadn't talked about this in advance, I wouldn't know that the negative 1 needs to be rejected. I'll show you what happens if we try to plug in each into the calculator and how only the 25 is going to work as a solution. So if I put in 25, I'm going to have to use change of base. Natural log of 25 divided by the natural log of the old base of 5 plus, well, 25 minus 24. You can actually put this in the parentheses, but hey, that's going to be 1. And hopefully you already know that the logarithm of 1 in any acceptable base is going to be 0. But log of 1 in base 5, you change your base, type it in this way. Got them added together, you get 2. Let's see if I can find where my error is. There we go. Whereas if I try to put in the negative 1, that's going to be a problem for both of these. Or even if you put it into one of them and you're taking the logarithm of a negative number, the calculator is going to bulk at us. Negative 1 minus 24 is negative 25. Got to use the negative sign, not the minus sign. And it's giving us a domain error. So our only solution here is the x equals 25. On this next one, instead of addition going on, we've got subtraction of separate logs. So I'm going to use the quotient rule for logarithms. The order of the subtraction mattered, so the order of the division matters. This one's a little different from the previous question, also in the fact that we've got logarithms on both sides. Remember that logarithmic functions are one-to-one, which would mean sides being functions. When you put in x, you get out 1y, for being a one-to-one function. Also, if the output, y, is the same, then the input has to be the same as well. That's going to allow us to drop off the natural log from both sides. I don't like that we've got a fraction here, so I'm going to multiply both sides by 3x minus 2 to get rid of the fraction on the left side. And on the right side, I'll have to distribute. Getting the like terms together, 7x minus 24x will be negative 17x. So I'll divide both sides by negative 17, which will cancel the negatives. And it cannot be reduced. See if that in fact checks. That denominator to make sure that we don't get something other than a positive. 3 times 16 over 17. Minus 2. Okay, we've got a positive there. And 7 times a positive is going to be positive. When we check, we should go back to the original equation, just like I did in the previous example. Natural log of 7 times 16 17ths. You can check that 3x minus 2 is going to be positive. I've already done that. 3 times 16 over 17 minus 2. Let's see how that compares to the natural log of 8. We may get a little round off error, we may not. Or as far as the calculator can show, it's coming up with exactly the same thing. And that's all I got. Hope it helps. See you in class.